All right, colleagues, friends, and online, importantly, a large online audience, thank you very much for joining. Welcome to ANU, welcome to Crawford School of Public Policy, acknowledging, of course, the First Nations on whose lands we meet and enjoy ourselves and work occasionally as well, the Ngunnawal and Ngambri people in our case here in Canberra. And we're delighted today to have a visitor from Canada principally, but from many places in the world generally, Dr. Chris Bataille, whose main affiliation is with the Columbia University Global Center on Energy, right? Chris has worked on the industry decarbonization realm for a very long time indeed, and I think for many years, maybe decades before the topic became one of general interest. And so we asked Chris today to present a kind of an introduction to global decarbonization options in heavy industry. And to do that on a topic which is, of course, very much in the public policy and industry eye in Australia, but to do so from an international perspective. It's oftentimes the case that we focus very heavily on a topic like this in Australia, where obviously there's huge opportunities. And we tend to think sometimes that this is an Australian issue, right, exclusively, which of course it is not. And so having Chris here today is a wonderful opportunity to get some of the global outlook on these topics. So Chris, I think you've got a sort of a half-hour presentation or thereabouts. And then we take the rest of the time for questions. Now, if you're online, feel free to pose questions in the chat. We'll have a look at that as we go. And then at the end of the talk, we'll put you up in the Zoom window on the screen as well. So we can use the raise hand feature there as well. Okay, over to you, Chris.
Okay, everybody. Thank you for coming here today, both to the folks in person and in online. Just by way of a little bit of an introduction, I gave this version of this, a shorter version of this talk in Adelaide a little over a week ago to the HITEM conference, focusing on more to the technical end and bringing a bit of a policy lens. And then I got to spend a little over a week driving across southern Australia, the coastline, until I got here. And I have a little bit of I have a bit of a hobby in economic history and economic development. It was just interesting seeing how that's played out in Australia and how close it is to Canada. One of the things that struck me is that there's been an economic revolution has occurred over the last 20, 25 years where a lot of iron ore and a lot of coal was sent to China, and basically hundreds and hundreds of millions of people were lifted from abject poverty up to the equivalent of middle class. It's the largest improvement in human welfare in human history, and it was largely enabled by steel coming from Australia. At the cost side of that is that emissions in China, both from electricity and steel and cement and what have you, went up over 10 gigatons. So it vastly accelerated us coming to the point where we've got to deal with. We thought we had till the 2050s, 2060s, and it has to be dealt with now. We're already breaching the 1.5 limit and heading towards 2C, so to land in that window. And it strikes me that Australia could very much, with its iron ore and its various other minerals, if it's done right, could very much have a role in the transformation of development and global development globally in a clean way. So anyway, it was just something that kind of came through my mind as I was driving along. Most of the folks in this room don't probably know this already, but as I said, emissions are still going up. They went up, I think, 1.3 or 1.7% last year. I was part of the UN GAP report, wrote the industry portion. If we're actually serious about landing in the 1.5 to 2C window, CO2 emissions have to go through a zero in 2055 and then go into the negatives and all GHGs by 2100. And what that means is industry has to. Prior to the Paris Agreement, most industrial sectors kind of went, yeah, we'll deal with that later this century. We're in the last 20% of emissions that everybody was talking about, minus 80%. But the world we're living in now is that if we are serious about 1.5 to 2C, the next generation of everything that's built has to be near zero emitting and heading towards negative. So it's a complete flip in terms of R&D, commercialization, and innovation. I always like to start with a couple of slides on where the emissions are in the global economy, just because people have a perception. We spend so much time on transport, right, which is 16.7%. We talk a lot about fossil fuel production, which is 8.9%. We talk about buildings, which is 7.6%. But the lion's share of emissions are from electricity. So you've got 23.4 plus 11.8% here, or 35, 36. And a third of all electricity that's made goes into the industrial sector. And then the direct CO2 from the industrial sector is 26% of emissions. And we've literally been ignoring this until a few years ago. So, with all the attention, it's good that we've been really paying a lot of attention to electricity, and it's good that we've been dealing with transport and buildings, what have you, but we really need to deal with this chunk right here. Where the emissions come from in the industrial sector, number one is iron and steel. If you count all fossil fuels that are oxidized on sites, it's somewhere between, in iron and steel processing sites, it's somewhere between 10 to 11% of CO2 emissions. Cement and lime comes in behind that, just roughly 8. Other industry is 5.1, and then you get chemicals, ammonia, and ferrous metals. Now, this may look strange to you coming from a highly developed country, right? Because most of your emissions, I guess you're guessing, would have been in here. This is the global view. As countries develop, like when you first hit about $1,000 to $2,000 per capita, the first two sectors that explode are steel and cement, because you've got to build a lot of infrastructure for water, sanitation, transport, everything. But then what happens when you hit about $10,000 to $15,000 per capita, those numbers fall down, and then other industry and chemicals go up really rapidly. Ammonia is pretty steady through most countries' development, and it's mostly going into fertilizers for food. So how do we do this? How do we take this, and how do we take this sector down to near zero, net zero, and then negative? These are the 6 broad strategies that we drew out in the chapter 11 of the last IPCC report. The first thing is just start with as much demand and material efficiency as possible. We know how to build bridges, build buildings, what have you, with about 20 to 30% less steel and concrete, and they will be just fine. You just have to have the architect and structural engineer thinking about it and working within existing building codes. Circularity, more recycling, and most of the practical circularity is in metals, just getting those rotating through the system with the least amount of contamination possible, and you'll see why that's important in a few minutes with steel. We always talk about energy efficiency. We tried not to talk about energy efficiency in the last industry chapter, but the reviewers forced us to bring it back in, consuming another 40 pages when we wanted the whole chapter to be just 40 pages. But anyway. I'll deal with that little problem off the side. Then there's just electrification and fuel switching with existing processes. We know how to electrify a lot of processes already. Electric boilers, heat pumps, what have you. The problem is, in most places, it's cheaper to use coal and natural gas than it is to use electricity, right? So that's just a spark spread difference. And the easiest way to get at that is either standards or carbon pricing, but it can be quite high. Gas is so cheap in North America, it would take hundreds and hundreds of dollars a ton carbon price in order to force that ratio around. So in effect, we're in a place where we kind of almost have to regulate to force the electrification of existing processes. Where the fun stuff starts coming in is process changes allowing you to use more electricity and hydrogen, or electricity indirectly with hydrogen. That becomes very important for steel, as we'll talk about in a few moments. And then you can't, whatever you think of CCS, it's our backstop. Okay, so it's the thing that we're going to need to work for the residual emissions and to get into the negatives. You cannot do negatives without geo-weathering. Without CCS of one form or another, or CDR. So it's our back. And so almost think of it as the goalie on our football team. Most of the folks here, one of the things I like to point out to folks is that we always think of hard to abate sectors, when most sectors are not one great big blob. They're a sequence of things that happen. In steel, 80 to 90% of the emissions happens at the very first step. When we're making primary steel, you bring in iron ore, you heat it to sinter it into little globules. You take the metallurgical coal and you heat it to get it down to a very high purity coke. Both of those produce a lot of emissions. Then you put it into the top of a blast furnace. And it gradually, the coke, first it provides heat, and then as carbon monoxide, it rips the oxygen off the iron ore, leaving you with liquid iron at the bottom of the blast furnace, which then moves on for processing into steel, which is just really the setting of the carbon level and removal of impurities. You then get to a point, the alloying or refining stand, and then you press it out into whatever shape or form you want. The other way that's 70% of global steel production today. The other 25% of it is scrap based, where you take older steel products. We usually melt it in an electric arc furnace, but sometimes it goes into a blast furnace. Then it too ends up at a refining stand, ends up in here. So we can keep most of this stuff in the steel industry, and it's the same for most sectors. We can keep most of the processing. You have to figure out what's the key process that's producing most of the emissions, and in this case, it's the blast furnace. It's a reduction of iron ore, and figure out a way to replace that with something that's low GHG. Now, there are at least 9 pathways, and I feel like every month or so, someone comes up with another one for eliminating emissions from iron ore reduction. I could literally spend an hour on this slide, but the key thing in this sector is we probably get about 30% reductions from material efficiency, just thinking about how we use steel, 30 to 40% from more high quality recycling, and you'll see how that pans out in the study we did. And about 30 to 40% is going to be the expensive iron ore reduction, where we use hydrogen, CCS, or use electricity directly to rip the oxygen off of iron ore. And there's many folks in this room probably do more detailed work than I do, but we have lots of options for doing this. Now, this is just a summary slide of a study we completed this year. It was a second round of the Net Zero Pathways, Net Zero Industry, Net Zero Pathways project. We took someone else's global facility database of all steelmaking facilities, like all over 1,000 of them, over half a megaton. And then we looked at how old they were, how long they'd be till the next renovation of the main primary reduction processes. And then we started with demand, and we built our own demand forecast based on development level and GDP per capita. And then we looked at how much scrap was available in each of these countries. But then we basically started the model to running, moving forward through time, meeting demand, seeing how much capacity was available, how much you had to ramp, what existing you had, adding as much scrap capacity or secondary recycling as possible. And you get pathways that work out. There's also trade in green iron, there's trade in steel products here. The main global picture is blast furnaces go from 70% down to about 5 to 10% by 2050. We're a little too late to the game to completely getting rid of these by 2050. We might be able to do it by 2055 to 2060. Unablated blast furnaces. Recycling goes from 25% in our modeling up to about 58%. The IEA heads up to about 48%. And then you got a certain amount of fresh iron, reduced iron in there to meet. And it looks different for every country, and it's different at different points in time. You'll see D and P, that's demand and production. And the difference between each one of those is the imports and exports, and the net imports and exports in each of the countries evolving through time. The two I'm going to bring your attention to here, you got China, who goes from just under a gigaton of steel production today down to about 500 to 600 megatons because demand is falling off. They're past that point where they need a lot of steel. And a lot of scrap is becoming available in China. And if they choose to gather it, sort it carefully, they can go up to using basically best available US technology, mini mill technology today, they can get up to very high recycled levels. And they almost auto-decarbonize without even needing a lot of reduced iron. Although they'll probably, that's one ideal case. India, on the other hand, goes from about 120, 130 megatons today to well over 400, right? And it may end up as a net exporter of steel without climate policy. It's all blast furnace based with coal, and they're a net exporter of about 50 megatons. But if we constrain them with climate policy, you end up with a mix of some scrap, some blast furnaces left, some scrap, and a lot of reduced iron. That's pulling on their electricity system. So you need a lot more clean electricity in the Indian system, which is going to require electricity market reform and everything else involved with it. But I'm more than happy to talk with folks about this study on other points. So, sorry.
I'm just setting
Yeah.
up additional broadcasts and facilities.
Yeah, so a key thing here is how do we make this possible? We built two sizes of climate club. The dark green is a narrow climate club, which was not enough to get to net zero. The lighter green was enough to get to net zero. And the key thing is it included what we call the green iron majors. It's countries that have a lot of high quality iron ore available to export, and they collect subsidies. They collect subsidies from the rest of the members for that. So the key thing is you have to have India in there, you have to have Brazil. If China was in, that would do it. If China built a club around itself, a green iron club around itself, we'd be done. But this was assuming a different political context. And you needed the ASEAN countries as well. I won't get into this too much, but again, you've got two sides of the climate club. You've got fairly significant, either through regulations or pricing. In the club, you need to rise to $100 to $300 per ton CO2 price equivalent of some sort or another, probably of some sort of tradable REC certificates, what have you. And outside the club, we've got $30 to $100 a ton. You've got a border carbon adjustment going in and out of the climate club and between the countries. And then a key thing here is we're subsidizing all reduced iron within the club at a rate of $100 a ton produced. Because of this, you get a big shift in global iron production. The reds are the BF-BOFs, the yellows are electric arc furnaces, the greens are the clean iron. A lot of steel production moves. China goes largely scrap, Europe goes mainly scrap with some reduced iron. But most of the new fresh reduced iron is in India, Africa, and South America. Now, this is the slide that will be of interest to this crowd. This is where a lot of the green HBI comes from. And these are the big green iron majors. So Brazil, Australia, Canada, South Africa, Ukraine, India, US, Guinea, and Venezuela. This club is defined by those who have conservative measurements, very conservative measurements of high quality of iron ore left. Okay, and we get up to the point where around 200, almost 300 megatons of steel production through HBI year by year. The biggest one by far is Brazil. We have India has a lot of high grade ore to work with. And then you get Australia. Now you'll notice that's about 50 to 60 megatons coming out of Australia, which is a lot less than what's coming out today. And it's mainly focused on the magnetite that's available. It's not the hematite and the goethite. If we took your study a year or two from now, and then included a lot more upgrading and beneficiation, this slab could be a whole lot larger, depending on what the cost of that beneficiation were. But this is all with very conservative estimate of what high grade DRI grade ore is available. Sorry, that's the steel. Any brief questions on the steel stuff before I move on to the cement and then to policy? Yeah. Okay. So again, the after steel, the next big sector you need to be concerned with in heavy industry is the cement sector. Again, most of the demand is going to be outside the OECD. You've got a gradually declining demand for cement and concrete in China. I would say that's even a bigger, in reality, it's a bigger decline. This estimates from 2018. India almost doubles and triples the amount of concrete that's required. And then you've got other, which is mainly Africa and ASEAN. Now, the key thing with the cement sector, and this is a beautiful article, it's Haber et al. 2020. I love the drawings. The key thing here is we tend to make bad cement. We tend to make very GHG intense cement with a lot of clinker in most of the OECD countries. just by using 3 or 4 sizes of aggregates, using dispersants to minimize the amount of cement you need in there to hold the sand and gravel together, you can probably get a 25%, 20 to 75% reduction in the amount of clinker you need, which effectively means a 25 to 75% reduction in the amount of CO2 you have, because that's where most of the emissions are from. And it's about using cement and concrete more smartly. There's a huge potential for material efficiency in this sector, but it needs to come through at the country level, at the municipal level. It needs to be allowed, it needs to be used by all the various firms. And a big part of this is just going to professional concrete mixing. It's not doing it in wheelbarrows, because that's where you get the really high CO2 intensity cement. The next big place that you get a lot of reductions is cementitious material substitutes. If you've got blast furnace slag, if you've got coal fly ash up to a certain point. But then you move on to things, there's a mixture, you can use a mixture of roughly 1/3 ground limestone and 2/3 calcined clays. That can be displace about half the clinker without affecting the ultimate performance of the cement, right? Using that, which costs roughly the same to make as with clinker, you can knock out another half of the emissions if you're starting at 100% OPC, depending on your clinker mix. It's not as much in China because they're down at 67% clinker mix, but they can go down from 67 to 50. Then you're at the point where you need CCS for the remaining clinker. And this is the one place I would argue that we really need CCS to work. Someone's got to either on the just straight on the limestone calcination stage and then find another heat source, or just bolting CCS on the back of the whole plant, which might be useful because that's where we burn all our medical waste and dioxins, what have you, in the OECD. That's where we need this to work. I helped with a French study where they have 25 cement plants in France that they expect to need. Only 5 of them are anywhere near CCS geology. And their idea was on those 5 plants, they'd put CCS and they'd make all the clinker, but then they'd ship that clinker by rail to the rest of the country where it would get ground up and mixed into various types of cement and made into concrete where it's needed. So ideally, if you do as much of this as possible, then as much of that as possible, you only need CCS on about 20 to 30% of the actual cement production. Then finally, hopefully down the road, we get an alternative means of getting calcium oxide, which is the precursor for making clinker. And there are many different groups. This is Brimstone and Sublime are 2 US groups. Sublime just got a whole bunch of money from Wholesome. One does it by acid leaching, the other does it by electrocatalytic separation of limestone into calcium oxide and CO2. But again, there's a lot of hype around these technologies. They promise everything, but they're still at the sort of TRL 3-4 level. They haven't gone through that point where they've spent hundreds of millions and billions of dollars to build a megaton level plant. So we need those to show up at some point so we don't have to put CCS on all the concrete plants globally, or cement plants. So now I could do a session on chemicals and what have you, but what I've got here is we're now going to focus on the policy of how do we get these things built, given that they tend to cost a lot more in CapEx and a lot more to run initially. So we're going to need to meet business case, political acceptance, and just transition tests for these things to work. First thing you're going to need is a multi-level policy commitment to transition to net zero GHG industry. And from what I can see, Australia is already there, which is really nice. This is not necessarily the case in a lot of other jurisdictions. In the US, I have to spend time just talking this through first, right? Explain to people why it's necessary. And then you've got a whole stakeholder thing you've got to do to pull it together. At least in Australia, there's the anticipation that it could be a big export market. And therefore, it's something that kind of holds together the political coalition. You're going to need building code, design, and recyclability policies for material efficiency and circularity. You want your municipalities and your states to at least allow low concrete and steel construction to occur, to allow architectural and structural steel firms to even consider this, because there's a whole chicken and egg problem where someone back in maybe a century ago, built a building with too little clinker in it and too many substitutes, and therefore they mandate 100% OPC. Right? And then we get stuck with that in the code, and you can't judiciously use it, like judiciously use substitutes to bring down the GHG intensity. And this is a city by city, state / by province fight everywhere around the world. And then you've got to educate the supply chain in using this stuff. So there's a huge amount of potential. It doesn't cost a lot, but there's a lot of political transaction costs. Once we start getting into the more expensive stuff, you're going to need a transition pathway planning process with all your key stakeholders to assess your strategic and technological options, competitive advantages, uncertainties, and arguably South Australia and Australia as a whole is in that space right now, and doing probably world leading work in that. This is where things start getting hard for the expensive stuff, for reduced iron, for clinker, for hydrogen, for ammonia, for methanol, for HVCs, for aluminum. We need to now target those key process technologies that need to be flipped. We need to go through the R&D and commercialization step. There's a lot of emphasis on this, and this is sort of TRL 1 through 4. But the key thing is, I think we're doing enough of this. We don't need to keep plowing more money into this. This is cheap to do. At high temp, they kept rolling out more and more technologies for eliminating emissions from calcination, other ways to use hematite or what have you. I think we're doing enough of this. Where we're running into trouble is we're not building lead markets to get those into real 100 kiloton, 500 kiloton, 1 megaton facilities. Like actually get the plants built. Right, so that they prove the concept works, and then the normal finance can flow into them, and that's where we're going to need all sorts of like production tax credits, investment tax credits, supply chain brand, bilaterals between first customers, maybe trade, and I'll get into this in a moment, tradable zero emissions material standards. But this is, we need to now make the jump out of TRL 3, 4 up into 5, 6, 7 to 8. And once you get to 8, you actually start making a product you can sell and generate revenue. So coming back to this thing here, with demand and material efficiency, circularity, and energy efficiency, a lot of this stuff is low cost, little chance of leakage. The barriers tend to be domestic, with some cost structure and agency issues. Trade policy and a lot of subsidization really isn't needed. It's more about grappling with the local market barriers. Once you get into this stuff, you're looking at significant added cost per unit, and it's usually traded, which immediately means you're taking on several dragons at once. You're going to need subsidies, you're going to need protected lead markets, and to protect them, you're going to need competitiveness policies. But like the Europeans ran through a whole dialogue where they initially exempted their steel, cement, and chemical sector from the EU ETS, or gave them a lot of free permits. But then when they wanted to tighten it so that they can meet the Fit for 55 goal, they had to talk about removing those permits, which freaked out those sectors. The only way you could get them to agree to it was moving on to a border carbon adjustment, or the CBAM discussion. That was the logical series of things that happened inside the EU that arrived at the European CBAM. But then once the Europeans said they were going to start looking at a CBAM, you had an explosion of protests globally. The Indian government freaked out. The American government freaked out. Suddenly, the Americans who are focusing on this whole supply subsidy side approach to policy suddenly ran into the fact that their turkey industries, if they were entering Europe, would have to pay CBAM, which they were probably not all that happy about. So we end up in a whole world of political complexity here. Just as a simple thing here. So for example, for cement, just using ground limestone, calcined clay replacements for clinker and cement reduces a lot of CO2 emissions, but has minimal cost impacts. Therefore, it's not a competitiveness issue. You don't have to worry about leakage. You don't have to worry about, hellacious trade issues. Once you add CCS and you start increasing the cost 50 to 100% to make clinker, yes, you've got a trade problem and a competitiveness issue. So this gets into some work that we did at Columbia over the last year, looking at what policies do we need to get these first of a kind, clinker plants, reduced iron plants, ammonia, methanol plants built. And what a colleague and I had done a lot of in Canada is build cash flow models around these things. The kind of cash flow models that firms actually use for making their investment decisions. So that when they're trying to assess whether or not they're going to make a profit, they assess in a discounted form through time, how much money do they have to put up front? Then when they build, how much do they have to put in? How much capital are they going to have to borrow? How much interest are they going to pay? How much taxes are they going to pay? What's the revenue going to come back on? And remember, all of this is getting discounted through time. Now, a big mistake most modelers make is they might start with a social discount rate at like 1, 2, 3% for assessing investment. That's not how firms think. They might use the financial cost of capital, 5, 6, 7%. That's not how firms think. They use discount rates typically up around 12 to 14% to assess this picture. And if it's a first of a kind, it's typically about 20 to 25%. That thing has to pay itself back in a few years, or they are simply not building it because of the risk. Okay, that is where that fundamental disconnect is where a lot of our conversation about carbon pricing and models and policy has gone wrong, because it misinterprets how firms actually make decisions. If you want them to build these things, you've got to help them cover their upfront capex risks, the years they take planning, and the fact that they might not get regulatory approval. You got to cover the extra capital they might have to borrow, because they're not getting this money at like, sort of typical 5, 6, 7%. Someone's charging them 10% for this thing. And then because these plants tend to cost more to operate, you've also got to help them cover the OPEX. So there's an increased CapEx charge at the front end, and there's an increased OPEX over time. So you might need to give, for the very first plants, they might need a huge CapEx lift through some sort of grant, and then they're going to need some sort of like production tax credit or something over time to keep them operating. That's unless you can find a customer willing to pay more for the commodity. Now, if someone is willing to pay 20 to 40% more for the reduced steel, or willing to pay double for the clinker, yeah, you don't need all that. But we don't have that today. We don't have markets. We don't have direct markets. Of the few successful occasions this has occurred, and this has been with some of the steel projects in Sweden, what's effectively happened is that the folks who wanted to build the steel plant got into a conversation with the end consumers of the steel, who not only provided capital, but took equity stakes in that green steel plant. And in the background, you had an $80 to $100 euro per ton carbon price operating in the background of these car companies. So they were reducing their exposure. So the only time we've been successful in doing this is when there has been a high carbon price, there's been lots of CapEx subsidies, there's been OpEx subsidies, and there's been equity ownership of the final bilateral contracting and equity ownership of the end consumer in the new steel facility. That is where it's been successful so far, right? Which is a very, very high bar. We also did some calculations. There's a very difficult. November 6th, we'll see. The world's going to take two paths, at least in this whole discussion. If it goes down the path, I hope it goes down. There's going to be an attempt to do an IRA 2. Where they start to inject the things that didn't get covered in IRA 1. And specifically, one of the things we've been looking at is what are the production tax credits or investment tax credits that might be needed for reduced iron, for clinker, for ammonia, for high-value chemicals, for methanol and ammonia. How much would you have to subsidize these things, given normal cash flow modeling and firm incentives to get these things built? These values up here, the little triangle is the normal cost per ton of these commodities. So you see over with steel, it's like $430 a ton. The 50th percentile PTC for a first plant, and this was done with Monte Carlo modeling, is about $312. It's a 75% subsidy to get this thing built, right? That's the first plant. After that, because the risk starts to fall very rapidly, these numbers start to fall very rapidly. So the very first facilities are going to need a ton of subsidy, and then it's going to back off. Another discussion I'm in is, can we use, instead of just offering blind subsidies, can we use contracts for difference in order to get firms to bid for the subsidy they require to get these plants built. And that way they reveal the actual cost might cost them to actually get these things built. But that's an ongoing discussion that's being done right now. What are we doing for time? 12:38.
You're still okay.
Yeah. Okay. Just an example, like coming back to our steel study here, this is an example of where things go right, hopefully. Right, so I'm going to draw your attention to this figure on the right here. That's the cost of steel, roughly $430 a ton. We impose our policy package. The cost of steel jumps to $480 to $500 per ton. We have a couple of different scenarios here, but they all have subsidies for green iron. But if you follow this S2 scenario here, you'll notice it goes up to 500. And then it comes down by 2050 because we've got economies of learning, economies of scale. The price of clean electricity is coming down in the background. These facilities can choose islanded renewable power, or they can pull off the utilities grid, or they can use CCS if they want to. They don't do a whole lot of that. But you've got the cost of electricity coming down, the cost of electrolyzers coming down, and a lot of learning happening within the DRI facilities. And it's down to the point where it's equivalent to BF steel by 2050. That's just our estimate according to our parameterization and how we structured the models and what happened. So you're going to need a big kick at the front end, really high subsidies and CapEx and OpEx support right at the beginning to get these things to happen. But then through time, as they start to get built, you're going to get learning, you're going to get economies of scale, and the support can come down. And eventually, hopefully, it's getting near the cost of making steel today. So if we want to transform industrial commodities affordably, we need to think transformation, not incremental change, with targeted policy supports at every stage. So back at this one. So how do we do this? I think for the very first plants, there's just no avoiding big CapEx and OpEx subsidization. Hopefully it's as economically as efficient as possible, which is where the CFD approach to setting PTCs comes in. But another thing that we've looked at is, could you set up a tradable credit system that pulls these things in existence? And we did a study for Climate Works in California. There's roughly 10 cement plants operating, megaton scale cement plants serving California. We took the idea of the zero emissions vehicle standard in California, where if you want to sell a car in California, you had it started at like for every 1,000 cars you sold, you had to redeem 1 car's worth of zero emissions vehicle credits, right? And then it rose to 2 and 5 and 10. So basically it was an idea of setting, it's a tradable performance standard to force, they used it to force zero emissions vehicles into existence. Could we use the same thing for cement? Right, so could we say for every ton of kilogram of clinker that's sold, could you get 100 grams has to be zero emissions, and the company selling it has to redeem that certificate. The only place they can get those certificates is being sold them by a plant that's making zero emissions clinker. So it's taking the logic of market and a regulatory instrument wrapped around that specific commodity and using it to pull the first plant into existence, and then you could keep on tightening until all tons or kilograms of clinker are zero emissions. But it's not an easy thing to sell or structure, and it took the Californians a couple of decades to get the ZEV to work properly. In the end, it kept Tesla alive, and Tesla is effectively what the Chinese car industry learned from, which eventually gave us commercial EVs as we see them today. So that was another thing that occurred to me. It's like, without Australian iron ore and coal, without the steel, like China imports 80% of its iron ore, right? And 80% of that comes from Australia. Had it not had access to Australian iron ore to develop, would they have been in a position to create the amazing PV and battery industry and EV industry that we have today? Again, enabled by American technology, initially developed in the 70s and 80s. Like, it's a whole circle of things that might not have happened if they hadn't started with that high emitting iron ore and coal, but that's a whole other speculatory exercise. You're going to need early retirement of long-lived, highly GHG intense facilities. Steel plants are endlessly renovatable, right? And a facility, basically the idea, like someone will keep, they can, if you don't force them to, they'll keep relining a blast furnace over and over and over again, every 10 to 15 years. And it will, and eventually you're going to have to force them out of existence, or force them to use some sort of zero GHG technology. Now, the rest of the facility can keep on operating. Sorry, I have a question. Oh, we had finished? Yeah, sorry. Supporting institutions, all your infrastructure, electricity, hydrogen, CCS, for workforce education. And just, this is the last slide on a just transition. How do we do that? We need to clear global rules for benchmark systems for green materials and intermediate inputs. Start with simple and robust, build up recycling networks in the least developed economies, move to EAF, secondary steelmaking, use of green iron. Concentration of strategic capital from northern countries for projects with time limit upfront, market-friendly lead market subsidies to allow these facilities to get built in developing countries where they're needed. And as many early deployments as possible should be in developing countries to meet growing demand and prove feasibility of the finance community. So in summary, this is all possible, but will require a lot of planning, cooperation, and very subtle stage, stringent and fair policy. So thank you.